In this lesson, we're going to look at concurrent programming. And in fact, the real world is concurrent. It's very natural. The real world is made of activities that all progress at their own pace independently. This is what concurrency is. The computing world is also concurrent, extremely concurrent. Let me show you 3 levels. First, the top level, the internet, distributed systems, computers linked by a network. In this kind of a system, a concurrent activity is called a computing node or a computer. And computing nodes all execute independently. The second level is the operating system. That is the set of programs that manage a single computer. In this setting, a concurrent activity is called a process. Operating systems manage sets of processes, and each process executes independently, can progress independently. The particular point about processes is that they have independent memory spaces. Each process has its own memory space that is separate from the other processes. And the final, the finest grain level is in the process. So a process, which is the execution of a single program, inside a process, we can have concurrent activities too. And these are called threads. And the point about threads is that they share the memory space. Whereas the processes have independent memory spaces, threads share memory space. So there's a different form of concurrent activity, but it's still concurrent. So concurrent programming in both the computing world and the real world is very natural. Many activities are naturally independent. It's very clear in the world. Every human being, for example, is already an independent activity. And independent activities, by that very fact, ipso facto, are concurrent. Independence means concurrency. So the question is, how can we write a program with many independent activities? Well, it's clear that there must be support from the programming language. The language we have seen up to now has no particular support for that. We would have to create a whole framework to do that, and that's essentially what we want to do by going to a new paradigm of concurrent programming. So what we want to do is write concurrent programs. A program which contains multiple activities that can all progress and all exist at the same time in the program. These activities are not always independent. They might communicate or synchronize with each other. So communication means that information passes from one activity to another, and synchronization means that one activity waits for the other one. It waits for the other one to perform some particular action. So this is called synchronization. So what can we do? In fact, concurrency as a general programming concept is or can be quite complicated. It introduces many difficulties, and we're going to talk about some of them in this lesson, the next lesson. The particular one, which is a source of many others, is called non-determinism. This is also leading to a difficulty called race conditions. Also, there are difficulties called reentrancy, deadlocks, live locks. How do you handle fairness? How do you handle shared data? Also, when you write concurrent algorithms where many activities have to work together, that can be complicated. For example, Java's synchronized objects, which are a form of monitor, are very hard to program with. Erlang's and Scala's actors are easier to program, but they still have race conditions, and they can still be complicated. You can hide some of these problems by using libraries, but the problems will always peek through. You cannot hide them completely. They are fundamental. And if you go farther than just concurrency, if you look at distributed programming where programs run on multiple machines, then it's even harder, because in addition to the concurrency, you have that the programs are separated, geographically separated into pieces. And a third step makes it even harder: partial failure. If you have a distributed system, what happens when one or a couple of the nodes fail? Or what happens when part of the network fails? And the whole system doesn't go down, a piece of the system goes down. And this is even harder to handle. So if concurrency by itself is already very hard, and these 2 extra steps make it even much harder than that, the question is, we should try to make concurrent programming as simple as possible. So one fundamental question, a kind of holy grail, can we make concurrent programming as easy as sequential programming? Probably many people would say no, but in fact it is possible if we choose the paradigm wisely. We will give up some expressiveness, but as we will see, this is not so important. In this course, we will see that the paradigm called deterministic data flow, which is in fact a form of functional programming, and all the techniques and nice properties of functional programming will move into deterministic data flow. So we will see that deterministic data flow is in fact as easy as sequential programming. So in the next subsection, we're going to talk about deterministic data flow.